sort of wasting time here. Sorry, guys. Last time. Where do we do? What do we do? We did strong approximation. Strong approximation in the adels. That is a fundamental domain for the action of Q on the adels is given by a choice. I mean, there's lots of choices, but we can take 0, 1 cross ZP. Okay, so any element of the adels can be moved by a rational number into here, and uniquely so.
Or
into the closure of this, yes. And if two things are in this thing, then okay. There was something I didn't actually like when we went from weaker approximation to weak approximation. So weaker approximation, I mean, this is not standard terminology. Weaker approximation was the statement that for all, so if you're given a finite set S and CP in ZP for P in S, given S finite, and CP in ZP, there exists, let me say, N in Z, and given an epsilon, and epsilon positive, there exists an N so that simultaneously you can get within epsilon of all of the CPs, right? And then so this was, the proof was just Chinese remainder theorem. Chinese remainder theorem. The weak approximation was to do the same thing given S finite, CP in QP, P in S, and given epsilon positive, we want to know that there exists a Q in Q such that simultaneously we can solve this, CP is less than epsilon. Okay, and then what I said was, well, you just multiply by P to the N and apply this, which is true, but it's a little bit more subtle than that. So I wanted to just get it right because we glossed over it. So proof, observe that this happens if and only if, so let's see, for each P, for all P in S, there exists some exponent EP positive such that CP times P to the EP, or to the minus, no, to the EP. I'm worried about negative powers of P. I want to move this into ZP. Okay, so now I let capital N be the product over the P's in S of P to the EP. Okay, just that's a finite product. I want to get all those together, and I want to let NP be N divided by P to the EP. So take out do all but the P one. Okay, this is an integer, of course, but as an element of this is in ZL for L different from sorry, it's in ZP. It's exactly right. It's in ZP. It's in ZP. Right. Right. It's in ZP because I've taken out that P part. In fact, it's in ZP cross. This has only things that are co-prime to P in it. So it's invertible as an element of ZP. Okay. And then what I want to do is apply, and then, okay, so this holds if and only if Q times P to the EP minus CP times P to the EP is less than epsilon times P to the minus EP because of the way that these p-adic absolute values work. Does that make sense?
So what you did was, oh yeah, you multiply.
I'm just saying multiply both sides of this by P to the EP, whose norm is P to the minus EP.
Right.
Okay. So now this is an integer, but it's not this integer that I need to approximate. So apply weaker approximation. WA is usually weak approximation. So I'm going to apply weaker approximation to the collection CP times P to the EP times NP. okay, with P and S. So I need a finite, weaker approximation needs a finite list of things in ZP, and I need an epsilon, and the epsilon is the minimum of epsilon P, epsilon times P to the minus EPs, whichever one is the smallest.
P to the EP times NP is just.
P to the EP times NP is just N,
Okay.
exactly right.
Okay.
But I've written it out this way.
Well, kind of obscure.
That's right. Well, if I write it the other way, it'll obscure the fact that this is an element of ZP. Yeah. Okay, so I apply weaker approximation to this double, to this pair. I need a bunch of elements of ZP. So these are all in.
So was that the problem last time? Or we didn't-
It wasn't a problem. I just said it very quickly. I said, oh, you just apply a weaker approximation after multiplying through by this, but it's a little bit more subtle because I want to get,
Refactor it like that.
yeah. And then this minimum, okay, is some epsilon. So we get an integer n such that n minus CP times P to the EP times NP is less than, it's the minimum of all of them. So in particular, it's less than epsilon times P to the minus EP. Okay, and now the Q, I need to show that there exists a Q. So now I use Q equals N divided by capital N. Okay, that's the point. I just wanted to make that more precise because this holds now. If I multiply by P to the minus EP, I get N times P to the minus EP minus CP times NP has P norm less than epsilon as desired. But now I can also multiply by the unit NP inverse. So if I multiply this by NP inverse and NP inverse has norm 1 because it's a unit. So this gives me a divided by NP and now I've approximated CP with Q. And this is exactly equal to Q. Because Q is little n over capital N and capital N is NP times P to the minus EP. Okay, just wanted to clarify that
So
little.
you use Q very much in the lean sort of.
That's exactly what yes. Okay, good. Then I also wanted to, we talked about ideles. So this is still review. We talked about the ideles, which is the multiplicative ideles. So this is the set of X in the ideles so that for all P, XP is in QP cross, in other words, just not 0. And for almost all P, that XP is actually in ZP cross. And we talked about how this has a topology, which is not topology is generated by the obvious thing, but the obvious thing that generates the topology is not the subspace. So it's stronger
So
than
we're choosing the coarser topology.
the finer. The
So
finer.
we're taking the subspace one.
No, the subspace one is too coarse. We can't see the things that we want to see.
Oh, I see.
So generated, just to recall, generated by products of UPs that are open in a finite set. So UP in QP cross
If your
open.
basis elements are smaller, then that's going to generate the finer. Yeah.
Yeah, so these are our basis elements. What I neglected to do is what is a fundamental domain? So Q cross, first of all, we should check that Q cross also embeds into A cross. Plane. Q minus 0. Why is this true? Joey already told us last time, I think. How come eventually, of course, this embedding is still the diagonal embedding. Why are you eventually in ZP cross? Not enough. The denominator is enough to get into ZP. I want to get into ZP cross and the numerator. Okay, there's only finitely many primes, finitely many.
Because if you like make the norm smaller, then all of a sudden you're not invertible one.
Right. In denominator, that gets us into ZP, and numerator. Eventually we run out of primes that cause any trouble, and now we're just norm 1 everywhere. and numerator, that gets us into ZP cross eventually. Okay, well, is this action? So we have an action. Now we have an action of Q cross on the ideles, where we take an X in, well, let's take a Q in Q cross, and it'll map X in the ideles to QX. What else can we do? We take X and we multiply it, right? So this is a group. This is a multiplicative group under multiplication. Multiplicative group. We have a subgroup. How's that subgroup going to act? By multiplication. Okay. Is this action discrete? Sorry? Whatever. It is abelian. Yes. Yeah, because I want to, well, this is like a G mod gamma versus G mod gamma thing. Yeah, I haven't decided which of these I prefer in different contexts. I mean, as a number theorist, it always has to be this one. So, okay, fine. I agree with you. Okay, is this action discrete? So now I can't speak about zero. Zero is not the thing that I want to look at.
Does discrete mean the only thing that does nothing is one?
Yeah, there's a better definition, which is discontinuity. An action is discontinuous if, when you have two compact sets, only finitely many motions of one set intersect the other. That's what it means for an action to be discontinuous. Discreteness isn't the best notion, but it's a good enough notion for us. Does there exist, given any point, does there exist an open set around that point containing no others?
No, there's an action.
With the picture,
Yeah. Does there exist a neighborhood around that point containing no other points?
So,
No.
okay. And so what I really want to say is Q cross discrete in A cross? Or is the action discontinuous? And it turns out that in some contexts, including this one, those are equivalent. So, but let me just say, i.e., is there an open set, which is why we need a topology, around not zero, but the multiplicative inverse, 1, which of course, 1 as a rational number means 1 of type R, 1 of type Q2, and so on, right? The diagonal embedding. Around this point, having no other Q star points in it. Can we think of such a thing?
So naively, this action seems to be like simpler than the additive one. Because like when you multiply, you're sort of like, you're seeing exactly where things can happen, right? At the times. Whereas additively, you might be, you have to look at like the expansion.
Yeah, well, ZP is a ring. So when you add two things in ZP, you still, the ZP means the absolute value is less than or equal to 1. And we have this super absolute value. Instead of a triangle inequality, it's the ultrametric inequality. So that's why ZP, unlike the integers, which are not if you add, well, integers aren't defined by something having absolute value less than or equal to 1. But ZP is. So in that sense, the addition doesn't bother you in the same way that multiplication doesn't bother you. But certainly, okay, if you have things of norm 1, then you multiply them together, you get something of norm 1, which is what it means to be in ZP cross. But all right, can we think of such a set? Is there an open set around 1? Joy's got one?
If you're in every ZP cross and you're a rational number, you can't have anything in your numerator or denominator.
Beautiful. Okay, so the hint is, we're supposed to take sets that eventually look like this. Well, if we just take all ZP crosses, then and what here? Maybe 1/2 to 2 or something. Just some nice open set around 1, which I've multiplicatively normalized. Try this. So this is U. then as Joy said, if Q is in U, well, then Q is in ZP cross for every P. So it has no numerators or denominators. Then the
There's no other Q cross point. Oh.
Yeah, can't you take instead of like put all of R cross in the first slot?
okay, good. Okay, let's take all of R cross. Ah, good. There's one thing that's wrong with putting all of R cross here, which is that we can't disambiguate 1 and -1. Yep, -1 is the only other guy that can go here, but indeed I can put all of R cross plus the connected component of R cross, right? So this is R cross plus. Okay, then if Q, by which I mean is a rational number, is in U, then its embedding into QP is in ZP, which means Q has no numerators or denominators dividing P. Has no P's in numerator, because otherwise you wouldn't be in ZP, nor the denominator, because otherwise you wouldn't be in, you'd have something to the left or to the right of the constant.
I see.
So if Q has no numerators or denominators, then Q is plus or minus 1. And we've eliminated -1, which implies Q is 1. So Q is the only such element. And in fact, so this set that we stumbled into
Landed into units of Q. Or even more.
yeah, Q is a field. So yeah, the things of absolute value 1 and Q. Yeah. Yeah. So this U, in fact, is a fundamental domain. This U is a fundamental domain for the action of Q star on A star. It's closely related. Yeah, certainly that's the direction we're headed. Okay. So why is that? Is that clear? Should I say theorem? Okay. So if certainly if I have two things, if X and Y, remember what it means to be a fundamental domain. If I have two things, okay, so this is what I think I called part 2 last time. If X and Y are in U, in the adels, and X is equal to Y times Q, I want to know that Q is equal to 1. And of course, then X is equal to Y. So look at X times Y inverse. Y is invertible. U is invertible, right? I can divide and so on. Well, this is in U, because all of the components of X were in ZP cross, all the components of Y were in ZP cross. This is in U. The only rational number, we're assuming that this is a rational number. The only rational number in U, this implies that XY inverse is equal to 1, which means Q is equal to 1. It's trivial. Yes, it's very nice. Okay, and why can you move any X into U, given any X infinity, X2, and so on in the multiplicative adels? How do I move? Does there exist a rational number Q such that Q times X is in U?
See the things where like there are numerators and denominators exactly the same.
It's exactly right. Exactly right. There are finitely many. There are finitely many P such that XP is not in ZP cross by the definition of the ideles for each such. Now, it might be because it's in QP and not in ZP, or it might be because it's in ZP but not in ZP cross. So I don't know if I need to multiply by a positive power of P or a negative power of P to get into ZP cross. For each such, there exists an exponent EP in Z, either positive or negative, such that P times e to the P times XP is in ZP cross.
For this part, this fundamental domain stuff specifically, we're not using any topology.
No, we're using we want to know that there's an open set. the fact that this is an open set that contains one. No, for the fundamental domain, no, well, yeah, again, the way I've defined fundamental domain is I want an open set so you can move into the closure of that open set.
Like, I'm just thinking about what would happen if we do this with the subspace topology. Right,
Here, you wouldn't feel the difference.
like, is that thing you wrote up there is also open in
Yes, because it's an infinite union of things that are intersection. Yeah, it's an intersection of open, so it's not open. Yeah.
So you'd have to like do something else, right?
This is, I think, one of the places where you immediately see that you run into trouble with the subspace topology.
Right, because I'm trying to see like where is it? Yeah. Why did we make this choice?
Yes, this is the like most important set when we're dealing with Q cross acting on A cross. So yes, we want this set to be open, not the subspace topology. Yeah.
Right, because otherwise, yeah, you'd have these issues of, right, here you can say, oh, there are only finitely many things we have to kill, and
Yes.
the other one,
Yes.
that's not necessarily the case at all. Well, on the basis
For
of
any,
the reason.
yeah, for any individual element, it is true. But there's no, on this open set, you see, the subspace topology still says you take whatever used to be an open set and you intersect it with A cross.
Right.
Just because you're in A cross, just because this X is in the ideles, means that all but finitely many P's are in ZP cross. So point by point, we're okay, even in the subspace topology.
I see. Because if you try to do everything for an entire open set. Then,
Right. And we want this set to be open. This is a fundamental domain for the action. It's like the fundamental domain in some sense. Here, you really don't have.
The fundamental domain is the same, but it's not an open set.
But it's not an open set if we don't give it the right topology.
So we go to subspace, then this is an email.
That's right.
That's kind of nasty.
So we go to the correct topology. Yeah. Okay. So it's clear. So then we let Q be equal to the product of these P's to the EPs, and then times plus or minus 1, depending on whether times, what is it? Just sine of X infinity times the sine of X infinity to make sure that we get so that when we multiply Q by then
It looks like a lot deeper than
X times Q. I guess I want to multiply it by, yeah, okay. The way I've normalized it is not a minus sign there and a minus sign there, but just then XP is in XQ. Okay. Any questions on why the sorry? Yes, closure, but the closure of U actually is U itself because I'm not allowed 0 or infinity. Yeah. Additively, we have to put the closure, but here we actually.
the nice open set.
Yes. Okay, so good. So I wanted to just get that out of the way. And now let's go back to where we were, because we started doing some Fourier analysis, or we were doing.
We define the character.
Okay, we defined the characters.
Are these gonna have, like,
Recall. This is
finite
still
volume?
recall. Oh my God, I'm still reviewing from last lecture. Yes.
Are these gonna have like finite volume in some sense?
Great question. Great question. Should I make this an exercise, or it's sort of so is this finite volume with respect to the product of the multiplicative measures? So what is the volume of all of these ZP crosses? 1. But on the real place, I have dx over x integrated from 0 to infinity.
Somehow, like, you won't find a volume, you need some sort of subgroup or something.
Yeah, you need a compact subset on which to integrate this, and that'll be an issue nearly immediate. Or you need the thing that you're integrating to be Schwartz.
Right. Enough
In this
case
variable.
that part wouldn't-
Okay, so we're still recalling we have a character. I think I called it EA. EA of x is a product over primes less than or equal to infinity. Let's call this EP of XP, where there's one little subtle thing for finite primes. EP of XP is e to the 2 pi I XP, as we already had. And E infinity of x infinity is e to the minus 2 pi I x infinity. Okay, and I think I claimed but didn't prove, if I recall correctly, I claimed that EA on a rational number, all Q in Q, EA on a rational number is 1. Okay, and indeed it suffices, so suffices to show that EA on 1 over P to the E is 1. Because anything else, any other rational number, okay, let me say why. Because if I have a rational number Q, which is n over P1 to the E1 times PK to the EK, let's spell this out a little bit. So so this is claim 1. Claim 1 is that the character is trivial on the, so i.e. this thing restricted to the rationals is identically 1. Inside that claim is another claim. That's a suffices tactic. It says suffices to show that on reciprocals of powers of primes, it's 1. Yes, yes, but it's a little more subtle than that. And it's, in fact, when I was thinking about this argument is when I said, I don't like how I treated weaker approximation to weak approximation. So let me show you why. If Q is this, let n be P1 to the E1 up to PK to the EK, and Nj is n divided by Pj to the Ej.
Right, the n in the numerator, does it have like different lines or?
Yes, with n being
And it's like co-prime?
yeah, in lowest terms.
Okay.
Yeah. And P1 through PK are co-prime. Okay. So let this be the denominator. Capital N is the denominator. Nj are n over P e to the Pj's. I claim, now we have 3 nested claims. I claim that there exist numbers, integers Bj, such that 1 over n can be written as B1 over P1 to the E1 plus Bk over Pk to the Ek. Why is that? Okay, proof of claim 3, which is inside claim 2, which is inside claim 1. I think not. I hope not. Oh boy, maybe. Jishan? Say it again? Chinese remainder theorem. Yes, the Chinese remainder theorem again, although it is Chinese remainder theorem, but it's
Like partial, right? I mean, it's sort of.
yeah, it's like a partial fraction decomposition. So let me multiply both sides by n. What I'm trying to, so what I want is a solution to, if I multiply everything by n, then I get 1 is equal to B1 times n divided by P1 to the E1, which is N1. B1 times N1 plus B2 times N2 plus Bk times Nk. Now again, yes, this is just the Chinese remainder theorem. This Bezout, I want a solution to the Bezout identity. The Bezout equation is the b's are unknown, the n's are given to me, and I know that the GCD of all the n's.
So this is just over the integers, right?
This is just over the integers. I know that the GCD of all the n's
And these
is
n,
1.
n sub k's is just dividing n out by the.
That's right.
Prime.
That's right.
Oh, yeah.
Okay, so how do you solve this? Okay, so claim 4, a solution exists, and it's just the Chinese remainder theorem. Claim 4, this can be solved, and it's just induction on Euclidean algorithm. Induction on Euclidean algorithm. Again, not everyone has seen this, so let me do an example and you'll see exactly how it goes. So for example, let's take n equal to 2 cubed 3 squared times 5, just to get some numbers there. Okay, this is P1, P2, P3. What's N1 is 3 squared times 5, and 1 is 3 squared times 5, and 2, I'm going to drop the second thing, is 2 cubed times 5, and 3 is, I'm going to drop the third guy, so 2 cubed times 3 squared. So far, so good. And so the way to solve this equation is to do it step by step. First, I'm going to find, now these two do have primes in common. N1 and N2 have a GCD, their GCD is 5. So first I want to find, step one, bless you, is solve N1, well, some coefficient. I don't want to call it B1. Let's call it D1. D1 times D2, N2 is equal to their GCD. Their GCD is 5. So this is 9 times 5, and this is 8 times 5. So actually, that's easy to solve. N1 minus N2 is equal to 5. Right? 9 5s minus 8 5s is 1 5. Okay, and now this is co-prime to N3. Step 2, and of course, step 2 is the step induction, the induction step, which you would do for however many terms there are, until you get to the last term where the GCD is 1. So you finally find a linear combination that gives you 1. Here we already have 5 is co-prime to whatever 2 cubed times 3 squared. I actually need to know what this is. 72. 9 times 8. 72. So what multiple of 72 is 1 off from a multiple of 5? Well, 72 squared is times 2 is 144, which is -1. So 145 minus 144 is 1. So I think if I take -2 and 3, and then what multiple of 5 gives me 145? 150 would be a multiple of 30. So this is 29. 29 times 5 equals 1. Am I doing this way too fast or way too slow? I can't tell. Either you're bored or I've lost you, or neither of the above, and I should just keep moving. 5 was this. This was 5. And so now we found a combination 29 times N1. What I mean, this is a hard thing if you didn't know how to do this, right? It's not entirely trivial. If you didn't know what linear combination of 45 and 40 and 72 gives you 1, how would you figure it out? But in fact, you do it just one at a time or 2 at a time, where each time you solve whatever the previous GCD was, you just plug it into the next. Yes, it's just the Euclidean algorithm, but souped up a little bit. -29 and 2, -2 and 3 is 1 in this case. Okay, proof by example. So that's claim 4. This can be solved. So that's claim 4. That's check mark sub 4. Now claim 3 is that I want to, claim 3 is that there exists such a thing. Well, claim 4 tells us you solve this equation, you divide everything by n. So actually that check mark settles 4 and 3. Okay. Now, claim 3 is about to say that why claim 2 suffices. Claim 2 is that it suffices to prove this, because then assume that that A of this is always 1. Then what is the character of Q? The character of Q is n over capital of N. Capital N, 1 over capital N, we just wrote as B1 over P1 to the E1 up to BK over PK to the EK, which means I can multiply both sides by n. The character is additive. We know that it's a homomorphism, additive homomorphism. So this is EA of n B1 over P1 to the E1 times EA, the character on BK times n over PK to the EK. Now each of these, this is an integer, so that pulls out also, because this is the sum of that many NB1s. And each of these is 1. Okay, so all we have to do is check it on. Okay, so now I think that's check mark 2. I claim that it suffices to check it on reciprocals of prime powers. And now the final claim is what happens on a reciprocal of prime power. So EA of 1 over P to the E is, there's only two places to check. It's an infinite product. At EA is the adelic character, which is the product of all the local characters. E sub p's are e to the 2 pi I xp, except for infinity, where it's e to the 2 pi I minus x infinity. So this number, 1 over p, they're all complex numbers. Yes, each of these. So the character is a map. This is a map from the adels into the unit complex circle. So yes, we can multiply all these. Now you have to worry. Just be careful adding the exponents. Oh,
Product of exponentials.
that's right. That's right.
Add all the exponents.
That's right. That's right. So on the adels, all I know is that eventually this is in ZP. But if you're in ZP, then these EPs are all ones. So there's no problem with convergence. This is a finite product. Maybe I should recall, this is a finite product. Finite product. Because these are in, almost all are in ZP. Yeah. Okay. So there's no issues with convergence.
Why is integer n be one?
So because n times n over p to the e is 1 over p to the e plus 1 over p to the e plus 1 over p to the e n times.
That's in.
Oh,
yeah.
Yep.
We're not assuming anything about integers, we're just adding it.
Yep. Yep. Just that integers occur by addition. Okay. And so so what happens here? So I get the infinity value. All of the other values are 1 except for the pth value of 1 over p to the e times 1 for all the other places. The infinity value is e to the 2 pi I 1 over the real number p to the e with a minus sign. The p-adic one, remember what the p-adic one does, it drops everything after, it drops all the integer part, the ZP part, and just takes the Laurent part, which here is 1 over p to the e. So that's e to the 2 pi I 1 over p to the e. Treated as a real number. And that product is 1. So I think that's claim 1 checked out. Okay, so that minus sign on the reals is exactly to kill off the plus sign at all the other places in exactly the same way that the adelic absolute value on the rationals comes out to 1, except for the 0.
Because the way the math worked again on like the key place was.
Yeah, so EP, yeah, if I have a generic number, a minus n, p to the minus n, up to a1, a minus 1, p to the minus 1, plus a0, plus a1p, and so on, the p exponential is just e to the 2 pi I times this whole number, except everything from here on is an integer. E to the 2 pi I of an integer is 1.
Right. And so what's happening is when you take a generic number and you're doing this for all primes, you just take its expansion.
Yes,
In every, right? And then
That's right. that's right.
And that's why we're.
Okay, so in this case, the only thing, there's not, all of these digits are 0 except the first digit is a 1, and I have a p to the minus something.
Right.
So that's all that's coming out here. 1 over that 1 times p to the minus e. Does that make sense? It might take a minute to think about to get used to.
So what were the 4 claims again?
Okay, so the 4 claims, let's look back. One claim was that you can solve Bezout's, this is called Bezout equation. Bezout equation. So if you hear people say, I mean, there's a more general version of what Bezout was doing, having to do with planes in affine space or something, but claim 3, in the sense of integers, this is what it boils down to. Claim 3 is like divisors. Okay. Claim 3 was that, okay, you take this Bezout identity, you divide by n, you get claim 3. It's a partial fraction decomposition on the level of prime factors. Then claim 2 was that if you could show that 1 over p to the e always exponentiates to 1, then so does any rational number. And claim one was that every rational number has exponential one, has adelic character one. In other words, the adelic characters, i.e., this EA is Q periodic in the sense that EA of X plus Q is EA of X. So it's periodic under additive translation by Q in the same way that the e to the 2 pi I n, e to the 2 pi X is invariant under translation by Z.
This is like really weird, but when you phrase it that way, it makes a lot of sense.
That's exactly what's going on. Okay, so we're getting closer and closer to defining a Fourier transform on the adels. Do I want to say something else first? Okay, so definition. A function f from the adels to C we'll call factorizable if there exists functions f, well, let's just say fp from qp to C.
Yes, another question, we talked about this already, but why would infinity the convention for like the real parts?
Yeah, so, okay, there are two conventions, in fact, that replace the minus sign here with the minus sign there. But as long as you make the infinite place negative, the opposite sign of whatever you make the p-adic place,
Oh,
you will have this feature.
I guess I was saying just like, why do we use the symbol infinity again? Just like.
Oh,
Yeah.
yes, the prime at infinity as opposed to the prime at 0 as
Right.
yeah, or the prime at -1. It's just,
No good reason, just
yeah, you want some
zero.
people
It's a
prefer
number
0,
in
the
the
prime
D,
0,
like-
yeah.
So you're saying P less than P. I guess you could say P greater than 0. and P greater than 0.
So when we were talking about the conductor is like how many times you have to add p to, so yeah, if you remember, there was the integers, the ring of integers, which is ZP, and then its maximal ideal, which is PZP, and the quotient is a finite field. And in that finite field, when you add 1 to itself p times, you get back to 0. How many times do you have to add 1 to itself in the integers to get back to 0?
So
Do you want to call that 0 or infinity?
So this is like a characteristic.
Yes, exactly.
Be like characteristics. Well,
Yeah, but we call it characteristic 0. But we say it's characteristic 0.
you're right.
Careful. P is not characteristic.
Right, that's right. That's right. Because if you add 1 to its, yeah, QP is character. Yeah. Okay. It's convenient to write, as opposed to saying P greater than or equal to 0. I don't know. That's the, yeah, I guess. It's anyway. This,
This one up in the is nicer, right? Yes, right. 0.
yeah, less than or equal to P. Yeah. Okay. So what does it mean for a function to be factorizable? So this is not just a trivial definition. I'm not just going to say if there exist these functions such that f of x is equal to a product of fp at xp. But I need one more condition, which is that for almost every prime, for almost every place, fp, when restricted to zp, is identically 1. And you might imagine why I would want such a condition. In particular, eventually this xp is in zp. And whatever is happening on fp is eventually only going to be evaluated on zp. And that means these are all finite products. Pointwise finite product. Does that make sense?
Almost.
Yeah. So that's what factorizable. When I say something's factorizable, it means I can write it as this kind of Euler type product. With the added restriction, I'll always want this. I don't want to deal with convergence. So I'll always assume that whatever these functions are, when you restrict them to ZP, they have to be identically 1. They might have, that doesn't mean that the functions are themselves supported on ZP. That's another definition. But factorizable so far just means that eventually on ZP, the functions, this decomposition evaluates to 1, so that for any given x in the adeles, this is a finite product. So this is a finite product for any fixed x in the adeles. Okay, good. What's an example of such a thing? Can we come up with a function that has this property? E is a good example. Yes. So yes, yeah, there are characteristic. Yes, but this function is actually not trivial on, very non-trivial function, and yet when restricted to ZPs, it is 1. And so that's okay. So this is a non-empty class of functions. Non-trivially non-empty class of functions. Yes. Okay. Fine. A function is called adelic Schwartz. Definition. F is called Schwartz. I mean, Schwartz, and some people remind you that it's not the Schwartz class of real functions, but the adelic Schwartz.
Nicer class.
Yes. If it is, and now I'll put in parentheses, a finite linear combination. Bless you. A finite linear combination of, if it is factorizable. So let's say F is a product of these F infinities, FPs, such that F infinity is Schwartz in the usual sense of the term. All derivatives can go to 0 faster than any polynomial.
For F infinity.
For F infinity, the real place. And FPs are Schwartz, meaning locally constant and compactly supported.
Linear combination of such functions? Or?
Yes. So if it's factorizable, then I want this, and then I allow finite linear combinations, C linear combinations of such things will be called Schwartz.
It's not factorizable, it's not Schwartz, adelic Schwartz function.
Well, the linear combination will not be factorizable. All I'm saying is I want to allow finite sums of things that look like this.
Oh, finite sums.
Finite sums of all factorizable. Right.
That's right.
You just write a generic one, like F is some product.
Yes. So F, let's say capital F is a sum, is a finite sum, Cj, Fj. That's right. As J goes from 1 to K, where each Fj is factorizable and Schwartz in this sense.
That's it.
That's it. Okay, so Schwartz means it's Schwartz at each place. The CJs are complex numbers, arbitrary complex numbers. The CJs are complex numbers. These map into C. These are all functions to C. Yes. Good, I wrote it. Okay. Then we can define integration. I think we can define an adelic integral over the adeles. So definition, given Schwartz.
Oh, I see. We integrated for like QP, but not for the product of all.
Yes.
Of
Given a Schwartz, I guess I'm now calling it capital F. Well, I want to define it on a component. How should I do this? Yeah. Yeah. Okay. Given a factorizable Schwartz. In other words, factorizable Schwartz. In other words, it's one of these, function F, which is a product of FPs, P less than infinity, with FPs having support in CP, which is compact in QP compact, and almost every P CP is equal to, or is contained in is enough, ZP. Okay,
Because CPs is what you find the confines of probably
yes,
for each.
for each P.
Support itself.
No, support itself compact, as we, yes. Because then these are themselves finite linear sums of indicator functions of open sets. If you recall that discussion. So what I want is that eventually this CP is contained in ZP. Then I can define then the definition of the integral of f d mu of the adels by definition is a product over p's less than or equal to infinity of the integral over qp fp xp d dxp. So let's think about this. Again, the purpose of this definition is to allow myself, first of all, to integrate, and second of all, to do so without worrying about convergence here. So the FPs are compactly supported. These are some compact sets in QP, but almost all of them are contained in ZP. To be factorizable, so almost all of these integrals are actually over ZP, not over QP. Factorizable means that FP is identically 1 on ZP. So restricted to CP, these are all 1. Okay. Now I'm doubting myself because do I want this equal to ZP?
Also, the condition CP contained in ZP together with all the finite many of those FPs are 1 on CP.
Is not consistent.
Well, no, together that requires that almost all CP for ZP, right?
Yes, it's not, there's no, yes,
So those are the same.
those are the same.
Right.
Yes. That's right. But then I shouldn't write contained in because
Yeah.
they really are equal. They have to be equal because I assume that the FPs were identically 1 on ZP, not 1 or 0, which would be the indicator function of some subset of ZP.
And how do they behave as CP?
Well, they're 0. Their support is ZP.
Oh.
So think about what this says. Yeah, because what I want, because the integral of 1 over ZP is 1. And so all but finitely many terms in this product are 1. This again is a finite product. Finite product.
I see. When the ZP, this is sort of by construction.
By construction. We're assuming, we're defining things so that we only get finite products. So we never have to deal with convergence. And it turns out that's enough. Those definitions are enough in order to do the things we want to do. I mean, I haven't told you what we want to do, but of course, what we want to do is construct GL1 out of morphic representations. Okay, then we can get to the adelic Fourier transform. Amazing. Any questions on this definition? Does this make sense? Teddy, you don't like something.
Does this coincide with some product measures that you put on the adels?
Yes. Yes, the Haar measure on the, so this is, okay, this is a very good point. The Haar measure on the adels that we're putting on this sort of implicitly / explicitly is the product measure. Now that product measure, the support of that product measure is the full unrestricted product of R's and QP's.
Unless you restrict it to the adels.
We have to restrict it to the adels, but actually we do even better than that. We only apply this to functions that are that are the indicator function of ZP for all but finitely many places.
So we're restricting ourselves to some.
Yes. So we're making our lives even much simpler. But you're right.
Is the Schwartz definition different from the Schwartz definition in the book that contains one extra condition?
It's so the extra, remind me what the Bruhad definition is.
That's the extra condition that shows factorizable functions is the characteristic function of ZP for almost all.
That's exactly what this is.
Is that exactly the same?
It's contained in there because in the definition of factorizable, yeah. So if you want to call this Bruhad Schwartz, I guess some people, Bruhad, I guess, was the one that worked out these kinds of things. the definition of factorizable is that you are identically one on ZP eventually. Now, if your support is inside ZP eventually, but you have to be one on ZP eventually, you have no other choice but to be the indicator function of ZP. So let's just make that explicit, i.e. FP is the indicator function of ZP for almost all P. Yeah. So it is the same definition, even though it doesn't immediately look it. Yeah. Then we can define a Fourier transform. Okay, so definition, given a Schwartz or Bruchhoff-Schwartz or adelic factorizable Bruchhoff-Schwartz, whatever you want to, Schwartz. Let's add adelic, let's add Bruchhoff, let's add nice or something, factorizable. And of course, you extend this by linearity to finite sums, finite linear combinations. Okay, given adelic Bruchhoff-Schwartz factorizable F, we define F hat of C in the adels by you integrate F of X, the adelic A of X, du of X over X in the adels.
This is symbolic because this is like very simple, right?
Well,
One of those, there's probably been some sort of secret.
Oh, yeah.
you would think so. You would think so.
Yeah.
Okay. Is this function C is in the adels? Is this function of the type that we're allowed to use our integration theory on? Why? Okay, other than Nick.
You wouldn't be doing this.
Fine. True. Yes, the psychology.
Wait, what was it?
The question is, I told you how we discussed how we're allowed to integrate functions that have this property, that it's eventually one, that it's eventually the indicator function on ZP. Now I'm taking that and I'm multiplying it by this character, which is definitely not one on, well, especially when I multiply it by this C. And so is this thing of the same type?
What do you mean by same type?
I'm only allowed to define this integral if the integrand is of Schwartz class. So, of course. Yes, okay, so certainly this is factorizable, right? That step one, this is factorizable. So let me write this question. Question is F times EA Schwartz.
I thought you were asking if that is.
I will also then ask if F hat is Schwartz, because of course I want the whole purpose of this is to invert the Fourier transform. But before I can even define F hat, I have to prove a theorem, which is that this integral makes sense. Was that?
Okay, good, go ahead.
Yeah. How do I make sense of this integral? First factorize it. Okay, so is this, yeah, the first step of being Schwartz is being factorizable, or I guess factorizable Schwartz. Yeah. Yes, this definitely does factorize. So this is equal to a product of FP EPs. For each one, can I define this integral, and is the integral identically one for all but finally many P? Okay, the infinite place we don't care about because it's all but finitely many. Right? At the infinite place, that's just one place. Okay, the infinite place is just one place. Yes. So we'll have to definitely use the fact that the C is in the adels.
So what are the properties that we know about these?
Right. Let's remember what FP was. FP, for all but finitely many P's, FP is the indicator function of ZP. what is the Fourier transform of FP? I guess I'm sort of answering the other question, which is this Schwartz? But what is the Fourier transform of remember we worked out, recall.
There's like a simple looking function.
Yes, if I take an indicator function of a plus p to the n zp, which is a typical open set in QP, we're now in local setting. If I take this indicator function and I take its Fourier transform, xc, you remember what we get?
There's like the negative version.
Yeah, e to the 2 pi I axc. So there's a character times the indicator function of c being in.
A plus p to the minus one.
There's no, the a moves into the character and the p turns into p to the minus n zp. So what's the Fourier transform of this? Of this indicator function? A is 0, so there's no character. N is 0, so it's itself. Okay, so that's one hint that moves us towards the yeah, exactly. It is the local Gaussian. It's its own Fourier transform. You see that? And so that's a hint that when we take this, we will get a Schwartz function, because all of its local factors are eventually 1. The indicator function on ZP. Well, that also tells us that we can evaluate this integral, because when we take this transform, so this is a question of whether Xi is in ZP, but eventually Xi is in ZP, because Xi is in the adeles. So eventually Xi is in ZP, and so this this integral will just be 1 for all the finally many places. Okay, does that make sense? Yes.
Not ZP to all the finite and
Right. So this is eventually identically 1. Yeah. Since where can I put this? I guess Vitaly Bergelson uses every little inch of the board, the fractal method of the board. So Xi eventually, CP is eventually in ZP. So this infinite product is finite. So this product is finite. Okay, and by this calculation, this implies, so this implies this, and this implies that f hat itself is Schwartz. F hat is Schwartz. At the real place, it's the standard theory of Fourier transforms of real Schwartz functions. You just differentiate by parts, integrate by parts, and at the finite places, eventually you are the indicator function of ZP, which is exactly what you do. Okay. Good. We have the Fourier transform, which means I can try to state adelic Poisson summation. Let me I'm assuming that you know that you've never seen these things before and you don't know why any of them are interesting. So before we do adelic Poisson summation, let's recall real. The goal is to construct the zeta function by an adelic Mellin transform.
Like what sort of information would that give us?
It'll give us the analytic continuation. And in the sense, in the adelic setting, it'll give us not just the analytic continuation, it'll give us simultaneously the Euler product formula.
Yes, what I mean is something what I mean is something a bit more limited than this. Like, you know, when you're dealing with a zeta function, right, it says a lot about prime numbers.
Yes.
Right? And prime numbers are these, like, you know, objects that anybody can deal with. Right?
Yes.
What sort of questions is this going to be answering that are like fundamental in this sense?
It will give us access to the zeta function. So the zeta function as originally defined is only defined in some half plane.
Right.
And how are we going to analytically continue it so that we can look at the zeros? So the zeros of the zeta function give us information on the primes. To get access to the zeros, we need analytic continuation. Riemann's method for that analytic continuation is to take Poisson summation formula, take its Mellin transform, and realize that as a functional equation for zeta. Question, Joy? Oh. And Tate's observation is that one can do this adelically, and one can do it in great generality. This is,
What does he hope to achieve with generalizing this?
there are all kinds of problems in, I mean, there's Artin's conjecture that when you take these Galois representations and you attach L functions to them, those L functions are holomorphic. And one way to see that is, I mean, this is what Langland's said, well, if those Galois representations are actually equal to the L functions of automorphic representations, for which we know, thanks to this method, that their L functions are holomorphic, that's one way to prove Artin's conjecture. And that's in fact how we know cases of Artin's conjecture. The Langland's tunnel theorem is a key instance of this, Jerry Tunnel's, one of his many main contributions, which was used in Wiles's proof of Fermat. So is that a very long-winded, I mean, that's a huge,
I think,
you know, what these things are good for. They're good for Fermat.
These things are eventually one, this thing is eventually useful.
Yes, this theorem is eventually useful. And of course, the real world says, what do you mean? It's useful because you proved Fermat. Like, how is that useful for me? Eventually useful for humanity, I'm not so sure. Although, yeah, that's right. That's right. I think so too. There's an old, you know, there's the old, the professor is teaching the fundamental theorem of calculus, and the kid raises his hand, you know, why do we need, professor, sorry, what do we need this for? It's like to save lives. And then the professor's proving Green's theorem, professor, this, what do we need this for? To save lives. Stokes' theorem, you know, is this also to save lives? Yes, of course. I'm sorry, how is this saving lives? You guys know the punchline?
No.
Keep idiots out of medical school. I'm definitely gonna have to edit that out. Anyway, yeah, how are we saving lives? Of course, no, how is this useful? And it's an oldie. Anyway.
So sort of like a rephrase the question, it's sort of like Diophantus would find this interesting.
I mean, Diophantus couldn't even begin to wrap his head around this stuff, but
I mean, like you could like solve or
yes. Oh, in the sense of yes, yes. Well, and 1,000 other tools, but yes, these are key ingredients. This, what we're trying to build up to is some of the key ingredients, for example, in the resolution of things like the congruent number problem, which was also Jerry's big contribution to this theory, and Fermat, and lots of other things. Right, well, I'm out of time, so instead of recall, upcoming, I have to explain to you Poisson summation, which I think I'll first do Poisson summation, which I'll first do over in the standard, in the more classical setting of R mod Z, and then we'll develop it on adelically. Yeah, does that make sense? And once we have that in place, then we're very close to automorphic representations on GL1. Adelic. Okay.